Okay, welcome to today's Innovation Hub webinar. So this is the fourth webinar of this spring installment. So before we start, I'll just give a very short introduction to our company and our series of webinars. So to begin with, this is just an intro to our company. So we are part of CTS, leading designer and manufacturer of products that sense, connect, and move. And we are, of course, in the division dealing with the piezoelectric ceramics, the so-called AMS division. But here you see our global footprint distributed over North America, Europe, and Asia. And at Ferroperm, we have started this Innovation Hub initiative, where we want to make contacts to people outside our company in other ways than the strictly commercial one. So part of this is a series of webinars, and I will just show the program of the webinar. So the fourth webinar, as I said, is today, and the title is Modeling of Piezoelectric Devices using SPICE and Finite element software. And our guest today is Klaus Brebøl from the company Limiel España. And Klaus has more than 20 years of experience with piezoelectric ceramics and transducers. So I'm looking very much forward to hearing his talk today. So now I will stop sharing and give the ball to you, Klaus, please.
Okay, let me see. I have to figure out how to get the... Can you see the screen now? Just a moment. Here we are. Okay, I hope you can see the screen now.
Yes.
Good. First of all, thank you, Erling, for the invitation. For me, this has always been a topic that I enjoy a lot, so I also enjoy to share it with others. And it is not going well. It will be a rather compressed presentation on practical advices on modeling systems containing piezoelectric materials. Before I begin to talk about the modeling, I will make a few introductional steps. And about piezo devices, a piezoelectric material, I see it as a bridge between the electrical and the mechanical world. We have the direct and the converse effect. That is, if you can imagine here, we have the red piezoelectric material, and then we have some electrodes, and we have a couple of wires going to our electronics, and similarly, we have a mechanical connection to the mechanical world outside. And then through these connections, we have energy flowing, and it can either flow from the mechanical side to the electric side or vice versa. And the conversion of energy takes place inside our material. So in order to handle this, actually, we need people who knows about electronics. We need some materials people that knows about piezoelectrics, and then also someone who can tell us about mechanical vibrations. And then on top of that, we have physics related with the particular topic we're dealing with, for instance, sensors or energy harvesters, power ultrasonic imaging. You can extend this list as long as you wish. And therefore, very few people can have an education that covers all the necessary fields to design a device. And you will have to you will have to use teamwork to have a success doing this. And modeling is actually part of a teamwork. It's part of facilitating the teamwork. But before we begin talking about modeling, I'll just mention that all models in this presentation are assumed to be operating in the linear range of the piezo materials. And this is not going to be a modeling course because the topic, there's no way it can be covered in just 1 hour. Instead, I will give some personal comments based on my experience from more than 20 years of successes and failures. You'll learn a lot from them. And let me begin by quoting George Box. He was a British statistician, and he used this remarks in several papers and books, and that is, all models are wrong, but some are useful. And I will use a slightly milder version and say your model should be adequate and used within its limits, which means that it should be as simple as possible, because then it's easier to handle, it's easier to understand, and most of all, it's easier to verify. At the same time, it should be as detailed as needed. And since simplifying means removing, did you remove something important? The only way you can know if you have got the right balance here is to use reality checks to ensure that your model is actually useful. But you should be beware of the quality of your checks. And I will bring another example from the world of statistics. This is from our teacher in statistics in the university. And he claimed that in Denmark, there was a 10-year period during which the number of children being born was well correlated with the number of white storks. Outside that period, the correlation was not so good, but it's not enough to have a good correlation coefficient. You need to make sure that your reality check is actually also a real check. As an example of what I do when I do modeling, I will show you this transformer. It's a disk with 3 concentric electrodes, and the electrode pattern is the same at the lower side of the disk. It all began as a finite element model, and once I was happy with the result of the simulations, the last simulations I did was just a moment. I have a here. The last simulation I did was this, showing the input impedance, the primary impedance of the transformer as a function of the resistive load on the output. And as you can see, when we go from a no load condition, a very high impedance, where we have a high Q resonator, and then with gradually lowering the resistance, we go to a low Q situation here. And again, that's around 100 ohms load. And then when we continue to short circuiting, we end up in a high Q condition again. And having seen that, it was time to make a prototype. And after having made the prototype, the same measurements was made in real life using an impedance analyzer. And you will see that our no load condition, we have the same behavior, a high Q resonator. And then when we short circuit it, we have a shift in frequency, but otherwise the same behavior, similarly to the simulation. And if we give it a 100 ohm load, we have this low Q curve here, which is also similar to the green curve here. So all in all, there is a nice match between the model and reality. And you can say, why not stop here? Because it is, you have your finite element model and you have your check that it is actually fitting very nicely. But I prefer to continue. So from the simulated impedance plots here, I create an equivalent circuit. And from this equivalent circuit, I create a similar impedance plot to the first one. And you can see again, there is a nice correlation between the two plots. So all in all, we here have 2 models that both fit nicely with reality. And what I want to say here is that finite element and equivalent circuit models are not alternatives. They are complementary, and hopefully you will understand that from the following. By modeling, why do we make models? Well, there's the design question. By modeling, we simplify our device in order to make it more manageable and easier to understand. Iterations in a computer is a lot faster than making real prototypes, so we can hopefully cover much more ground using a model instead of using real prototypes. And if we have the right model, then we can also get more information from it that we can get from prototypes, because using finite element, we can actually, in quotation, see what is inside a device during operation. So we get more information in shorter time by using a good model. And finally, we can also use the model for tolerance analysis. So we can check if our product is, it can be manufactured using normal tolerances, nothing exotic. So that's one part of modeling. But there's another one, and that is it can be used to improve communication between different project groups. We have just heard that we need quite a lot of different expertises involved in this. So as an example, I'll show you an ultrasonic milling machine. Yep. This is the spindle of a milling machine. You have the tool here. It's being rotated by the spindle. And at the same time, since this is an ultrasonic machine, we have a power transducer in here, which is being supplied with electric power through a rotating transformer. That is a transformer with a stationary primary and a rotating secondary, and there is an air gap here.
Also, just a minute. We are not seeing the machine. We came back to the overview. Yeah.
Okay, just a moment. Just a moment. What do we do here? There must be a place where I can select this screen, I guess. New share.
Yeah.
Yep.
Oh, yeah.
Now I have two versions of that. I'll try to. Can you see it now?
Yeah.
Okay.
That's fine.
I will just start it again. So just to repeat, the tool being rotated by the spindle here, ultrasonic power transducer that will vibrate the tool, and then a power supply coming here through a rotating transformer, stationary winding, rotating winding, and the power flow into the transducer. And the whole idea is that you have this vibration here, so you can use it when you are milling brittle materials like technical ceramics or optical glass or whatever. Now I have to figure out how to get out of this. Just a moment. Can you see the
the
memory map
overview
now?
Yeah.
Okay.
Yeah.
So now I'm trying to show you a patent application. Let's see if I need to. Can you see it?
Yes.
Okay. So the system is being described in this patent application. We have the spindle unit over here with a transformer and a feedback loop and a block diagram of some electronics, including a power amplifier here. And another thing which were in that application was this. I don't know if you can see it now, a sketch of a transducer.
Yes.
So this looks like a traditional sandwich transducer with a front metal mass, a backing metal mass, and some piezoelectric rings squeezed in between. And we have the secondary coil of the rotating transformer and a feedback loop and everything. You put this on the desk of the electronic engineers, and there will be a deep silence, followed by some will run out of the door screaming. So that's probably not a good idea. But if you instead put this, I hope you can see an equivalent circuit now.
Yes.
Okay. If you put this equivalent circuit saying we have a power transducer here with a static capacitance and the dynamic branch over here, it's being supplied through this transformer. You have to notice that the coupling coefficient is a bit low. It should be around or more than 0.9 normally. But that's the air gap in the rotating transformer. But please take this into account. We will ask you to design an amplifier that can provide XX watts over here. So that's the ultrasonic power that we use in our process. And for the electronic engineers, of course, this will be completely natural and they will begin to work. So to communicate through to the electronic engineers is a lot easier using equivalent circuits than to use mechanical drawings. But the process goes both ways, because electronic people will normally know about circuit analysis and circuit synthesis and filter design and high frequency amplifiers. So they will be able to see things that may otherwise escape your how you see it when you just see the mechanical design. So it's something that works both ways, and you will have a feedback that can help you to understand and change your design if necessary. And then we arrive to the point where we are going to talk about today's two different ways of making models. And I'll begin with the finite element modeling, because it is in here I am reaching I show something that can be used later in the equivalent circuit models. So let's begin here. And the positive thing you can say about finite element simulations are that they are as good as it gets. It's probably the most flexible and accurate way of modeling piezoelectric devices, and sometimes it's even the only possible. The negative is that it's hard on resources, both money and time. You need expensive software and hardware, and it's another discipline that it takes time to learn. But once you have decided that it's worthwhile, then the question is how to get started. And in general, I will say, if you're completely new to this, just a moment. If you're completely new to this, you should find a good book to read, because you probably know a lot about piezo ceramics, but you are a bit thin on finite element simulations, and therefore to get an overview. For me, this book helped a lot. Building Better Products with Finite Element Analysis by Adams and Ashkenazi. But and it was very useful, although there was not a single word about piezoelectricity. But again, this is not what you need at this point. This book is from 1999, so comments on hardware are probably a bit outdated, and I don't know if you can find more recent ones, but I will say that it doesn't really matter, because the basics are well presented in this one. The other thing you have to read is the software manual of your finite element software, but this is like Word and Excel. You read what you must know, and the rest you leave for later, because otherwise you get stuck. Can you find a finite element tutor? You are lucky, and it'll be a great help. In all circumstances, you should begin by modeling devices that you know as real products, so you can reality check the results. This is probably the most important part of modeling, that is, all the time be able to check that your model is valid. And to make this model, you will need a physical model, and you will need some material data to enter into the model. And I have chosen to separate those two things, but let's begin with a physical model. And naturally, what should be included in the model? Remember, as simple as possible, as detailed as needed. Any unnecessary geometric details should be removed, and CAD files will normally need quite a lot of cleaning if you get your design as that. But the more simple your model is, the better you can see the principle behind the functioning, and the quicker it will simulate. Once you have your geometry finished, it's also a question about meshing, and you will have to remember that solving time is roughly proportional to the square of the number of nodes. A good choice is 5 to 10 nodes per wavelength at the highest frequency in your model. So if you model the resonance you're operating at, that's one density, but if you want to include the third harmonic, well, then suddenly you will add 3 times more nodes per dimension that you are including, so you may end up with a considerably larger figure. On the other hand, if you fall out at the other end with a low quality mesh, too few nodes or other problems, you may end up increasing solving time, although you have very few nodes. So it's a compromise. And sometimes you may even choose to do manual meshing to get a faster converging solution and a better quality of your results. A very efficient way of reducing the size of your model is to choose either to make 3D or to cut down on the size of the model by using symmetry. And symmetry is a very efficient way to cut down the size of your model. But you should also remember that it's a filter. So if you use symmetry, you lose all the asymmetry which are in your model. And the way to do this is to exploit symmetry as much as possible to get started. And once you are closer to your final solution, you begin to include 3D simulations to avoid asymmetric surprises in a more unpleasant moment. The transformer I showed you at the beginning, it's here again. And this is the impedance plot, the measurement of the open condition and the short circuit condition. And the short circuit condition, you can see here that actually in the phase we have a small bump here, and there is similarly a small deviation in the magnitude of the impedance. And I didn't really look into it at the beginning because who cares about how the transformer works when it's short circuit? But then later I decided to take a second look, and this is how the prototypes are being made. Oops, I'm going to stop this just a moment. It's actually a disc with a full electrode, and then we just grind a little bit through the electrode to make the electrode pattern that we want. And once it has been made on the top side, then we flop over the device and you get the similar pattern on the back side. However, a machine like this is not super precise. And in the end, it turned out that our small thing here is an asymmetry because the trace was 200 of a millimeter deeper in the back side than it was in the front side. So this could not be modeled as long as I was using a symmetry condition that so I only modeled the upper half of the transducer and assumed that the lower half was similar. But once I included that the lower half was 200 of a millimeter deeper into the 1 millimeter thick disc, this appeared due to a bending mode. So the symmetry conditions can camouflage a lot, and even small details can be of importance. So much about the model. Another thing is material data, because a model can only be as good as the data it's being based on. And what you normally see in finite element software, that's a database where there will also be piezo data if your finite element software is for handling that. But I will give you a warning, and that is that if you are above 100 kilohertz, you may have a problem because most of these databases are based on data measured according to industrial standards, and they are all what I prefer to call low frequency standards. Erling showed you this in the first webinar. I'm just going to repeat it briefly. We need this data matrix, and due to the symmetry of the material, which is caused by the polling process, we have a lot of zeros. But there's still left 5 independent elastic constants, 3 independent piezoelectric constants, and 2 independent piezoelectric constants. And the normal way to characterize this is to use what we can call the resonance method, because it has, you only need an impedance analyzer or something even more simple to measure impedance, and then you can do it. You measure the electric impedance versus frequency in a selection of resonators that has a single mode of vibration, which can be described by as few parameters as possible. And then afterwards, you can calculate the relevant parameters. The standard suggests 4 items, which we have here: a plate, a disc, and a slim rod, and a shear plate. And with these 4 items and 5 measurements, it gives a step-by-step procedure for calculating a complete set of material coefficients. That sounds intriguing, but there are problems related to that. And as an example of that, I will give you an example with respect to the shear. The shear characterization is done using, of course, a shear resonator. And this is being poled lengthwise, and we have electrodes under the two major surfaces. Here you can see a measured impedance plot. And it's obvious that we have several spurious modes here. So first of all, the coupling coefficient is being calculated from measured frequency. That's a point here and here, the two measured frequencies. And it may not be particularly easy to characterize that with such an amount of spurious modes. The recommended way to avoid that in the standards are that you increase the length over thickness ratio, and then you get a damped curve where you can more easily identify the maximum impedance and the minimum impedance. Another parameter that has to be measured is the dielectric, the permittivity, and the dielectric loss. But the standard recommend that this is being measured at 1 kilohertz. And that means that we measure some parameters at 1 kilohertz. We measure the resonant at 3 megahertz, or maybe even higher. You can see here, due to the thinning down of the sample, we are now at 8 megahertz almost. And then from the combination of these parameters, we are capable of calculating the D15, the parameter that we were looking for. But all in all, this process only gives you the dielectric loss and the mechanical losses, not the piezoelectric losses. And if you look at the curves here, you will see that if we are planning to simulate something around 3 megahertz, well, the curve at 8 megahertz looks like it has lower Q and therefore higher losses than in the frequency range where we would like to operate. So the losses that we get from this are also a bit dubious. What Erling mentioned as the Alemanni method is using the same impedance measurement, complex impedance measurement, but instead it's looking at the two peaks given by the real part of the admittance and the real part of the impedance. And the impedance of this kind of resonance can be described by this equation. And from solving this numerically, the measured impedance and this set of parameters, we can extract the dielectric parameter, the piezoelectric parameter, and the elastic parameter. And this means that we can, since we are calculating with complex figures, we get these results as complex figures. That is, that we do not only get the magnitude, but we also get the losses of these figures. We get both the dielectric loss, the piezoelectric loss, and the mechanical loss. Furthermore, from this curve, we can recalculate the shape of what we have just been extracting, and therefore we get this line as a measure for how close we are to the measured data points, both for the resonance, both for the series resonance and the parallel resonance. So we have a quality criteria built in our parameter extraction. So the Alemanni method has certain advantages already, but it's possible to improve it. One thing is that when you measure on 4 different samples, you have a certain spread of parameters. I mean, the 4 different samples are not completely identical, and therefore it can be problematic to combine them into one data set. And using a bit more complicated mathematics in the Alemanni method, we have, or the plate resonator has been removed, so it's only 3 resonators instead of 4. Another thing is that we changed the shear sample. So instead of having a sample which is poled in length mode, we choose a sample which is poled in thickness mode, like here, and with electrodes on the end surfaces. This has the consequence that we can thin down this sample, thus changing the length over thickness ratio without having to do anything about the electrodes. So we can do this as a continuous process. The advantage of using this sample is that it's easier to polarize. It's the same poling condition as for the disk. So probably we have a more homogeneous set of samples and therefore a better homogeneity in the data we extract. And by the possibility of making this continuous change in the aspect ratio, we can adjust our spurious modes. In real life, this looks, well, first let me show you the shear mode of our item here. We have a thickness poled shear resonator, that means thickness poled, electrodes here and electrodes on the side you cannot see over here. And the item is moving like this, shear and shear. And if you look at the fixed mesh behind, you will see, or the fixed grid, you will see that the amount of movement is almost constant all the way across. Except when we approach the edge, then there's a coupling to other modes. And this all depends on the resonance of the different modes, whether they couple a lot or very few. This curve shows the impedance measurements I was talking about before for a 2 millimeter thick sample, 15 by 15 millimeters, so an aspect ratio of 7.5. And you can see here we have 2 clean resonances. If we thin down the sample in steps of 200 of a millimeter, there is something in here. And as now we have a thickness of 1.82, suddenly this resonance breaks up in 2 resonances. And the assumption that we have both in the resonance method and in the Alemanni is that we only have one resonance condition. So this is poison for the accuracy in our parameter extraction. What is more interesting, or equally interesting, is that if we continue thinning down the sample, you will see that these plate modes here, they are reasonably constant, but the shear modes are moving as the sample gets thinner and thinner. So the coupling is not constant. It's not that we can say that above a certain aspect ratio, we are free of any coupling. It's more that we should search for a certain aspect ratio, and then we will have good possibilities to extract our data. If you look at this, here we have the double resonance that was 1.8 millimeter in thickness. If we then thin down the sample, you'll see here at 1.62 millimeters, we have 2 very clean resonances, which we use for extracting the parameter. And the aspect ratio is not 1 in 10 or 1 in 20. It is only 1 in 9. So we have a frequency range which is similar to the one that we plan to use for our modeling. This was presented in a paper in 2008. And at that time, if you looked in the literature, there were suggestions that an aspect ratio of 5:1 would be okay, an aspect ratio of 27:1 or 20:1 or up to 62:1. But if we look at this, you can see here the aspect ratio and the correlation factor that we can get. So actually this repeats itself over and over again. And we can pick a place where which is close to the resonance area we would like to work with, the resonant frequency we would like to work with, and nevertheless get good results or reasonable results. So it's more complicated, but I will say it is worthwhile. So much about finite element for the moment. But no, sorry, I forgot one thing. This was shear. But there is another thing, and that is that shear is actually influencing thickness modes also. So it's not an excuse that you're not making accelerometers, you're not operating with shear, you're only working with thickness mode. No, because here this was rather surprising. But if we make a simulation, a finite element simulation of the the three samples, the rod, the disk in planar mode, the distance thickness mode, and the shear, then these two matches nicely. Here in thickness mode, we have the measured value here, we have the finite element simulation here for the resonant frequency, over here for the parallel resonance, and you'll see that they are 4 to 5% low. And this is using a data set based on the standard shear plate. If we instead use a data set on the thickness pole shear, which we have adjusted in thickness to obtain a better quality of parameters, suddenly it's not only those two who are okay, but the thickness mode is also showing a good match. And if we look at the simulation of the shear, we are actually beginning to see that we can simulate the spurious modes as well as the main mode. So all in all, a better quality of shear also influence the simulation of the thickness mode. And that's a bit surprising, of course, but if you think about it, what happens is that a plate vibrating in thickness due to the Poisson ratio also show vibrations in the radial direction, and therefore what you must have inside are areas with shear movement, and therefore the shear coefficients are of importance also for the thickness mode, because the thickness mode is not a clean thickness mode. So much about finite element modeling. Another thing was the equivalent circuit modeling. And the background for that is that both vibrating mechanical systems and electronic circuits can be described by a set of differential equations. There is a big theoretical toolbox available for analysis and synthesis of electronic circuits. This toolbox can also be used on mechanical systems if you can transfer the different parts of the mechanical equations into their electrical analogies. There is an excellent article, excellent paper written by Arthur Balato from 2001. It covers a lot of the topic. You can, no, you're gonna see it here, but it's some 50-something pages, and it's for sure worthwhile to read. It may be a bit overwhelming, but I would like to show you one remark from this. And that is this, the following. The power of carrying over a network description and microwave electromagnetic techniques of analysis may be illustrated here by a few remarks. We noted previously that it wasn't until 1954 that it was realized that the plate waves, he's talking about mechanical waves, could be decomposed into pairs of longitudinal and shear waves reflecting at the boundaries, whereas the analytic solution was given 65 years earlier. The reason for the time span is largely because the physical features of the problem are obscured by the mathematics. So what he says loud and clear here is that equivalent circuits can bring clarification to a problem that is correctly described, but just in a way that is not so obvious what goes on. And therefore it's worthwhile to use them. Apart from this, that they can be used as to clarify certain things, they also facilitates the connection of your device to whatever electronic circuit that you plan to use, and you can model everything in, for instance, a SPICE simulator. That was the background. The implementation, there are two ways that we normally implement these circuits, and one is using discrete components where we have the, it'll come later, sorry. Or we use a transmission line model. Here we have the resonator in the as an LC circuit. Here we have the resonator as a transmission line. The discrete component circuits are only valid around the resonant frequency which are being pictured by this LC circuit. And this means that you can only use it for frequency domain analysis around that frequency. Outside the neighborhood, it will not be valid. Therefore, you cannot use it for time domain impulses either, because impulses normally contain not just one frequency, but a whole spectrum of frequencies, and most likely outside what can be dealt with by this model. If you instead use the transmission line model, the resonator here will not only give you the fundamental resonance, but also the overtones. And therefore, it will deal correctly with not only the frequency signals, but also with the impulses in the time domain analysis. This circuit shown here is the Redwood circuit. It has inherited the rather counterintuitive negative capacitance. That is counterintuitive, and it can also be a problem in some SPICE simulators. But there are other possibilities, for instance, the KLM model, where we have a full transmission line here again, half a wavelength long, and then we have the electronic components here, which are of more normal character, no negative capacitance. You can check Berlato's paper, and then you can see which model is suitable for you. As a final example, I would like to of what you can do using modeling. I would like to show you an example of a 200 kilohertz transducer. I think Erling mentioned something like this in an earlier webinar. And the topic, as I remember, it was a disk 20 millimeters in diameter, and we should have a thickness mode of 200 kilohertz with a narrow tolerance. This is difficult because the 200 kilohertz means that the thickness will be around 10 millimeters. So 20 millimeters diameter, 10 millimeters thickness, those two modes are going to couple. And instead of having sorry, I have a, okay, no, yeah. Instead of having just one radial mode and one thickness mode, we have a mesh of modes that couples with each other. And here, for instance, finite element is a fantastic tool because you can, in very brief time, make what-if simulations. For a thin disk geometry, Kp and Kt are material parameters, you can say. But for a thick disk like this, the effective coupling is a component parameter that depends on the dimension of the actual component. And therefore you are free to, you can play with these dimensions, and you can actually optimize the coupling coefficients. And what it looks like here after a few simulations is something like this. We have the original disk in the background, and then we have a ring simulated here. This is the blue curve, which I don't know if you can see it. I have something on top of this, but okay, here we are. The original disk was 20 millimeters in diameter and around 10 in thickness. The ring is 20 millimeters in diameter again, a little bit less in thickness, and there is a hole in the disk of approximately 9 millimeters. And by adjusting these two parameters, it's possible to change the coupling coefficient, because we are adjusting the coupling between the width and the thickness mode of the ring. So we can adjust the coupling coefficient, and we can adjust the position of the resonant frequency to match with the 200 kilohertz that we wanted. And this is where, I mean, this is a small task, but it's a place where the finite element is extremely useful, because in very short time, you can do an optimization process, a lot of what if, and get a result like you wanted. You can also do this in real world trial and error, but it will take a lot more resources. The equivalent circuit modeling cannot be used, because we are actually changing the apparent elasticity of the ring by changing the dimensions, and therefore it's actually the result we are looking for that has to enter into the model, and that's simply not possible. But all in all, of the three methods here, finite element analysis is by far the fastest and therefore the most economical of them. The equivalent circuit modeling should not be forgotten, because it's still a great help for the interface to the electronics. In summary, finite element models and equivalent circuit models are not alternatives, they are complementary. Finite element analysis is heavy on resources, but it's a very capable tool. Its major drawback is the lack of clarity, and creating equivalent circuits for the simulations may help in this aspect. All the results should be checked against reality, not just at the end, but preferably also during the design process. The equivalent circuit models are great help when creating interface to electronics used together with the device. Clear one-dimensional topologies or one degree of freedom resonators are the easiest to implement, and component values can be calculated. When we go to 3D items or items with coupled resonances, thing gets more obscure, and it's therefore better analyzed using FEA. Comparing of electrical impedance versus frequency plots for the finite element models, the equivalent circuit models, and the actual measurements is an effective way to check the validity of the models. And finally, the quality of a model depends on the quality of the data and assumptions it's based on. So I must have cut something, because I am considerably faster than I was with the last test I made. But that gives some room for questions.
Yes, very good. Thanks a lot, Klaus. I think this was a really interesting and very clear presentation, and I think it's really nice to get sort of the overall view of comparing two complementary methods, as you were saying. We already have the first question. So this question is, how close can the pulse echo voltage predicted from the KLM model match real experiments?
Oof, that's not exactly my specialty. So I think I'll have to pass on that one, because it's I have been doing quite a lot of finite element simulation. I have also been doing quite a lot of equivalent circuit modeling, but the KLM model is something that you typically see among medical transducers, and medical devices of that kind is not exactly what I have been involved in. So I will have to pass on that.
That's quite okay. So while we are waiting for the next question from the audience, I was thinking one of the things you mentioned, you know, is the losses, something that is quite interesting to both of us. And sometimes when discussing with people, I've met people who think that mechanical losses and dielectric losses are really enough for describing the piezoelectric world, and they are very skeptical about piezoelectric losses. I think I'm on your side, but can you give some arguments? What you think? How sure can we be of piezoelectric losses, and what do they mean in practice compared to the other types of losses? Do you have some comments on that?
Yeah, for sure. First of all, for me, it would be very strange if we have an energy conversion which is lossless. I mean, that's, I would like to see any other place in nature where this happens. So I'm convinced that piezoelectric losses are there, and they are for real. I mean, you can say there are mathematical indications from our models. We don't know if the model is correct, but let's assume that the model is correct. And then the general idea that we cannot have an energy conversion process running in a lossless manner outside very special examples. So yes, I believe that there are piezoelectric losses. And for me, it's, of course, the most important part is the total amount of losses in a model. And what you see there, now I have been working quite a bit with piezoelectric transformers, and they are limited by the heating, at least the step-down transformers. So what is important is the total loss, and you may get away with saying, well, the dielectric losses are like this, and mechanical losses are like that, and we don't really need the energy, the piezoelectric losses. But once you have an efficient transformer that can transfer a lot of power in a small volume, that is with a high power density, then you will have to know also the piezoelectric losses. At least that's my experience. If you want to model that, you will have to know piezoelectric losses.
Yeah, very good. So I have a couple of questions more already. So the first one on my list is, would finite element analysis be beneficial for doing 3 megahertz PCT ceramics material model simulation? Do you understand the question?
There are a lot of possibilities here, but
yeah.
I will say for sure. I mean, depending on what you try to model, I will say that there is nothing that you cannot model. Maybe you won't need finite element to model it, but on the other hand, if you use finite element model, you can always optimize your model to model whatever you are doing. It's just a question of how many resources you have to spend on it.
Yeah, very good. Next question from my colleague Martin in the Czech Republic. So what modeling software do you use? You went quickly over that one, so maybe you now get a chance to mention that.
Yes, I bought Attila around year 2000 and have been using that ever since. Because what happens once you begin with a program is that you sort of get stuck with it. You need to have a really good reason to change it. And since it's not an office package, for a small company, it's quite an investment, and therefore I have been using that ever since.
Yeah.
I know that there are other packages, and I have a certain experience with how can I say, I have met COMSOL and I have met ANSYS with customers, and now we were talking about losses, and as far as I have understood, then COMSOL will be able to represent all 3 types of losses. I'm not so sure about ANSYS, but again, it depends on the kind of model, what you need to model, if you will consider that a serious drawback or not.
Okay. And yeah,
I may add, by the way, that for the equivalent circuit modeling, actually there is a free SPICE simulator, LT SPICE, that you can get from Analog Devices, and it's an excellent simulator, and it costs absolutely nothing. So
yeah,
if you don't have any other SPICE simulator in-house, I'll suggest that you begin there. With finite element programs, it's a much more complicated process.
Yeah. I just wrote the name LT SPICE on the chat if somebody didn't catch it. So thank you for that, Klaus. And the last question that's open now is how can fatigue affect piezoelectric beams operation? And which method is best for simulation in this subject? So the question of fatigue in the case of piezoelectric beams, do you have a comment to that?
I have a comment, but it will be, I have not done fatigue measurements, but if you have a component and are interested in the fatigue behavior of it, my suggestion will be that you have to test it in real life, because you cannot find material data on it. And for doing so, I would expect that it will be enough to run your component in real life conditions and then observe how it deteriorates. And this you can do through the equivalent circuit modeling. You don't need finite elements for that. But on the other hand, if you can gain ideas of the fatigue behavior during this, then you can try to introduce it into your finite element simulation, and this way be able to model other devices. That will be my approach to that question.
Yeah, I see what you mean. And in principle, if you could do a realistic fatigue and then get your hands on the sample again, in principle, you could even let's say try to determine modified fatigued parameters and put them into the model and maybe learn something from that. Yeah.
And then you can gradually improve your model doing that.
Yeah.
But I guess that fatigue is a difficult problem. I guess you can also see a certain spread in parameters there. I mean, I have a certain experience with fatigue in metals for high power transducers. And for instance, if you buy the same titanium alloy from the same supplier, but it has been machined in different ways, you will see different fatigue behavior. So I think it's quite a can of worms that you are opening if you begin to do this. So yeah. Good luck.
Yeah, good. I think there are no more open questions, so maybe I get to ask a second one. When you showed this, of course, this is a very interesting point also for me, this alternative shear geometry, and it was interesting to see that when you change the aspect ratio gradually, you sort of at a periodic behavior. So I was wondering this period that you see, for example, the distance between two maximum, let's say, values. Does that have a physical meaning? Have you thought about that?
Yeah, it does, because where were we? Just a moment. You have the length of the plate, and in that length you have a number. You have say n half wavelengths, and then you have n plus 1, n plus 2, n plus 3 every time you go through this periodic behavior.
Okay.
And this means that the longer plate you have, probably the closer these will be, because there's a big difference between having 10 and 11, 12 half wavelengths and having 101, 102, 103. So by using an extreme or a larger, at least, length or thickness ratio, you are probably ending up in the solution that is given by the more traditional methods. But this you do at the cost of increased losses, because you are at the same time increasing the frequency, because you normally do this by thinning down the plate. If you have a length of your plate of 15 millimeters, what do you need? 30 kilovolts to pole it. So you don't want to pole much higher than 30 kilovolts, I guess. Then you thin down the plate to make a higher aspect ratio. But if you want to stay at the same frequency range and to get your data in the frequency range that you're interested in, then what you really should do was to extend the plate, for instance, 4 times, but then you also have to increase your available voltage by 4 times, 120 kilovolts. And that's probably not a good idea. So I think it has a physical meaning, and I think there is a physical meaning why, I think there is a physical meaning why you cannot use the traditional aspect ratio solution, because you will automatically be pushed to higher frequencies, where with this, where we optimize, you can stay at the frequencies where you frequency where you are at the moment.
Yeah,
I hope that's clear.
Yeah, I think that really makes sense. Okay, I think we will end the webinar. We have done a full hour now, so thank you very much, Klaus. Very interesting, and I hope that people in the audience also learned a lot from this. So to everybody, I'll just say thank you for attending, and please, when you quit the webinar, don't be too quick. Just take a few moments just to do the little evaluation, and maybe if you have ideas for future subjects for our autumn series of webinars, please put them there. And for example, this emphasis on finite element analysis this year came from some input from other users, so it actually works. So thank you very much for now. Thank you to Klaus, and looking forward to seeing you in the autumn. Bye bye.
Bye bye. Thank you, Erling.